All right, so let's get out a piece of notebook paper or some kind of paper you have. And let me throw a couple of review problems up here. And let's make sure that we are all good to go on some of the stuff that we've talked about the last couple of days. So I'm going to put 4 functions up here on the board. And you are going to tell me if they are even, odd, or neither. And you're going to support that algebraically. So in other words, I'm not going with a gut feeling. I want support. In other words, prove it to me. Show me algebraically why these guys are even, odd, or neither. So before we do that, let's do a real quick recap of what does it mean to be an even function? Exactly. So f of x is exactly the same as f of negative x. So if you plug in a negative x, and the answer, after you go through all the steps, the answer comes out to be the same as the original, you are even. What does it mean to be odd? If you put in your negative number, your output becomes the opposite. So changing the sign on the input is going to change the sign on the output. So basically, with problems like this, you have one thing to do. Evaluate this. Find f of negative x. If it ends up equaling the original problem, you're even. If it ends up equaling the opposite of the original problem, you are odd. If it ends up equaling some other random thing, then it is neither, right? So right now, get easy. That's what you're going to do for these 4 problems.
You just put like 1 in for x, right?
You put in negative x. You put in negative x. If we're going to do this formally supporting our answer, we put in negative x.
Looks like it.
Are you reaching some conclusions? Declan?
Neither, odd.
Neither.
Odd.
What about this one?
Odd.
Oh, odd.
Oh, I didn't do the third one was odd. I didn't
Okay, you got neither for this one. So did
That's what I
I.
got.
Because when I put in negative x, this is what I got, and this is what I was supposed to get. I got neither here. Because if it were odd, I should have gotten the exact opposite, and I didn't. If it were even, I should have gotten the identical thing, and I didn't. So this is neither. Does everybody understand that? Okay. Would you say for this one neither? He got neither for this one also? Because again, if it was even, this should have matched this, and it doesn't. If it was odd, I should have gotten the exact opposite, which I didn't. So that's another neither. He got, this is the odd one, he got odd for this one. Because when he plugged in negative x, look at what happened. He got exactly the opposite of what he started with. Change the sign on input, change the sign on output. And then what happened on this one? What did you get here? Even, because when I changed the sign on x, it didn't matter. That one is an even. All right, we solid?
So just when I'm solving algebraically, I just plug in 1 and negative 1. Is that also an okay way to do it, or should I plug in negative x?
Negative x.
Okay.
Because we're supposed to be showing that it holds for all values of x, not just one particular.
Okay.
So, absolutely in a pinch, yeah, that logic's good. Right, if we're doing this formally, we really need these x's.
Also, what's like the first two where it's just like a number at the end? Is there any chance that could ever be even or odd? 'Cause
Oh,
like,
this has just a number at the end.
oh yeah, I guess it's not the same thing.
Okay, all right, next, review problem. I'm gonna draw a picture, you're gonna draw it too on your notebook paper there. I'm gonna draw a picture as best I can, it's not gonna be perfect. And let's see, I got a point here. I got a point here. Okay, so there it is, let's sketch that as best you can. By the way, that's a polynomial. It has a restricted domain because did you notice the solid dot right down here? Normally polynomials have arrows on both ends because they go on forever and ever. But this is a polynomial. When you graph a polynomial, it's going to be an unbroken hill and valley thing. Just up and down, up and down, up and down. Okay, here are my questions. I want you to find the relative. What's another word for relative? Relative means the same as local. So relative or local min, max, and give me x equals. And then absolute min, absolute max, give me the x values where that happens. And then after you're done with that, I want you to tell me if the rate of change is increasing or decreasing on these intervals. These are intervals. These aren't points, these are intervals. So I wonder if the rate of change is increasing or decreasing on those intervals.
mean, like half of it I'd say is increasing.
Are we done? So we're done with all of it? All right, let's go through it then. So what, here's a relative minimum. Remember, you can have more than one. So your relative minimums would be -4, 0. We're looking at X values. So -4, 0, and 3. Would you agree with that?
Yeah.
Do I have, well, I know minimums. Do I have an absolute minimum? My absolute minimum is where X is -4. And the minimum value looks like it's -3, sort of, anyway. All right, relative maximum. Do I have any relative maximums? -2 and 2. Do I have any absolute maximums? No, because of that arrow right there. Or this thing's shooting up into space. All right, so my picture being what it is, let's see if we can figure out what's going on. From -2 to -1, that clearly looks concave down, which means my rate of change is decreasing. From 2 to 3, it sort of looks like, as you pointed out, there has to be a point of inflection in there somewhere, right? Could the point of inflection be at about 2? So probably if I had to say from 2 to 3, I would say concave up, increasing. And then 1 to 2, well, 1 to 2, wait a minute, that's 2.5, isn't it? Because this was 2. Okay, so cancel that. The point of inflection is at 2.5, roughly, 2.5. So from 2 to 3, I am definitely doing both. Because this is the point 2, 5 approximately, and this is the point 3, 1 approximately. So that point of inflection would be somewhere in between, as you pointed out. And then 1, 2 is going to have exactly the same thing, because this part of the curve is concave up, and this part is concave down, so that's both also. It has parts of it that are both. Alright, that's what happens when there's something. Alright, is that okay? Alright, one more quick review problem. I have a polynomial whose roots are 1 plus I, 3i with multiplicity 2, 4, and -3 with multiplicity 3. So I got some crazy thing out there, and these are the roots. What is the least degree that this polynomial could have? What is the least degree that it could have? Somebody said 18? Wow, okay. 10? 7? What? 9?
Wait, I take back the 18.
Okay. Renege on the 18. 9. Got a couple votes for 9.
Hey, I have
A couple votes for 10.
10.
All right, let's take a look at it and see.
10.
We know that right here, we have accounted for 3 roots.
You got the red too.
Right? And right here, we have accounted for 1. Now this is where things get a little crazy. If 3i happens twice, then so does negative 3i. So this really accounts for 4 roots, the 2 3i's and the 2 negative 3i's. And then if 1 plus I is a root, so is 1 minus I, so that accounts for 2?
Yeah.
So what does that add up to? 10, you're the winners, 10's the winner. You guys have said 18, 7, and 9, you see what went wrong?
Yeah, is that Jolly Rancher?
Does 10 get a Jolly Rancher?
That was pretty good.
Alright, are we good on that? Alright, so let's get our notes out.
She dodged the question.
Let's get our notes out.
Play again, please.
One of the things you learn as a teacher is how to ignore.
Use the no strategy.
Alright, so we're on notes 1.6. Notes 1.6. So we're skipping through the pages we're gonna do tomorrow, or we'll do some of it tomorrow. A lot of this we've already talked about. The end behavior of a function describes how a function behaves as it moves infinitely to the right and to the left. Alright? So we talked about this specifically when we talked about some of our BFFs. You remember the logarithmic function? You remember what it looks like? Think about that. ln x. What does it look like? It has an asymptote at 0. It comes up from the bottom, up and out like this, right? Remember that? And when we discussed its end behavior, we said, as we went to the right, our picture went up. But it has no end behavior to the left, has none, because what happens? It has an asymptote at 0. And end behavior describes infinite movement both ways. And the logarithm doesn't go infinitely that way, so it has no end behavior in that direction. Polynomials, because over their regular domain, which is all real numbers, they will always have end behavior, right? Because they're going to go on forever and ever and ever. All right. End behavior is what happens to y as x increases or decreases without bounds. So we've already talked about our notation. Anytime end behavior is part of the conversation, this will be our notation. Right? This means what happens to my y's as x goes all the way to the right. And this means what happens to my y's as x goes all the way to the left. Okay. Describe the end behavior verbally and using limit notation. All right, so as we go to the left, how are we going to say this verbally? As x decreases, what does y do? Increases. So if we're describing this in words, picture A, as x decreases, that is, goes to the left, actually, I'm pointing the wrong way, that it goes to the left, y is increasing. Left behavior limit statement. As x approaches negative infinity, the limit of f of x is positive infinity. This is for picture A. Right behavior verbally. As x increases, y decreases. So as x goes to the right, y goes down. So there is your end behavior. That picture right there describes a function, negative coefficient x odd degree. Because normal odd degree functions have this behavior, just like the cubing. They start down and end up. If you put a negative in front of it, it's gonna start up and end down. That is gonna be a negative odd. All right, what about B? As x decreases, we're going to the left now, x is decreasing, y is increasing. So as x goes to negative infinity, y is going up. As x increases, y increases. So as x goes to the right, we're still going up. Picture B describes a classic even degree polynomial with a positive coefficient. Evens, I think I talked about this yesterday, evens are above. That's how evens are. Put a negative in front of it and then it will be down, down. But even degree functions, I keep saying even, I mean even degree, not necessarily even functions, but even degree polynomials are going to always be above or down, down. They're in behavior matches. Odds are the opposite. Odd degrees are the opposite. All right, let's get some of your examples up here. Sketch a polynomial with the following end behaviors. And let's not use a BFF. Let's get a little creative. So this one is down, down, and this one is down. So my volunteers, come on up. And this one, this one is positive, it's negative. It's also negative, okay? So this one positive is positive. Then here we got polynomial. That we have that same behavior, but with this increase in there, let's move it around. Look at this, very creative. Is it right? Is that exactly the kind of end behavior we want? Down, down? Which means, what can you tell me about this polynomial? It has a degree that is even and a coefficient, leading coefficient that is negative. Right? All right, is this one right? This is classic cube. Is that right?
No.
So its degree is odd, and its leading coefficient is positive, because that's exactly what they look like. Perfect. With polynomial equations, it is easiest to find the end behavior. Well, what do you think? I really don't care. I get what he's trying to say here, but I don't necessarily think of it this way. But I think it's easier to look on the right. the right side is always going to go up if the leading coefficient is positive. Think about it for a minute. If you are an even degree with a positive coefficient, you're going to be going up. If you're an odd degree with a positive coefficient, you're also going to be going up. So the right side is always going to go up if the leading coefficient is positive. And it's always going to go down. Oh wait, goes down if the leading coefficient is positive, and goes, wait, if the leading coefficient's negative, it goes down over here. I mean, it goes like this, right? If the leading coefficient's negative and it's odd, but if it's even, it looks like this if the leading coefficient's negative. So how are we going to answer that? The right side goes down if the leading coefficient is, or goes down if the leading coefficient is negative and the degree is even. But if the leading coefficient, oh, I see. No, the right side is going to go down, or no, go. I get myself all messed up. If the leading coefficient is positive, the right side is always going to go up. Yeah, the right side, I'm looking at the left side. The right side is always going to go up if the leading coefficient is positive. Because if it's an odd degree, it goes up. If it's a even degree, it also goes up. So the right side's going to go up if the leading degree, or we already talked about that, if the leading coefficient is positive. If the leading coefficient is negative, what's the right side going to do? Go down. If the leading coefficient is negative, the right side is going to go down no matter what. So the right side will always go up if the coefficient is positive, and it will always go down if the coefficient is negative. All right. Does that make sense? Let's say it again. The right side will always go up if the leading coefficient is positive, and it will always go down if the leading coefficient is negative. Now, the left side is the one that's a little confusing. The left side goes in the same direction as the right if the degree is even. But the left side's going to go in the opposite direction of the right if the degree is odd. So one more time. The right side is going to go up if the coefficient's positive, down if the coefficient's negative. The left side is going to match the right if you're even, and it's going to be opposite of the right if you are odd. Okay, so tell me about 4x to the 5th. The right side will be up, and the left side will be down. 1/2 x to the 4th. Right side up, left side up. What about C? Right side down, left side down. D. Right side down, left side up. E, right side down, left side up. And F. Right side down, right side down, and left side up. because if you multiply out of, you would have a negative x cubed. And a negative x cubed means the right side's down and the left side would be up. Write limit statements for the end behavior. Alright, so we're no more of this down up stuff. Now we gotta use our limit notation. So negative 3x to the 4. Negative 3x to the 4. It's a negative even, so it's going to, on the right side, it's going to be down. And also on the left side. Down, down. For negative even. Is that okay with everybody? And how about the other one? This one is odd positive degree, or odd positive leading coefficient. So on the right side, it's up, and on the left side, it is down. Okay. Now, I don't think you need a graphing calculator to tell me the end behavior of letter A. What is the end behavior of letter A? Both up, yep. Would everybody agree with that? It's a little travel. Now, these other ones are kind of funky, so go ahead, get your calculator out. B and C are not polynomials. Oh, we need to talk about this because that was a homework question that some of you, most of you, all of you didn't catch. These are not polynomials. Can somebody tell me, remember, what does a polynomial look like when you graph it? One, I don't look, just that's a polynomial. Tell me why B, in example 5b, why it's not a polynomial. It has an asymptote. And when you hit an asymptote, very good on packet, -1, what does that mean? Are you going to be able to draw some nice continuous function? No, you're going to be broken. It's not a polynomial. And the one in the homework, and it was definitely tricky on my part, but the one in the homework, I asked you about this thing. Now, tell me about that right there.
That's weird. You gotta flip it upside
That's
down.
7 over x cubed.
Yeah.
And as soon as you put 7 over x cubed, what have you done? You put in an asymptote, right? Because if you have an x in the denominator, then x isn't going to be able to be 0, right? And that means you don't have a polynomial. To be a polynomial, you can't have variables in the denominator, which means you can't have negative exponents. Are you clear on that? All right. So go ahead and graph the one we're doing and see if you can figure out what its end behavior is. We're graphing this on our calculator, and we know it's going to have an asymptote at -1. Does this one have a horizontal asymptote? Where? Vertical's the -1. Horizontal's at 2.
back up. Yeah, it's just like when I'm plugging up the point, it's like, it's just like, cause like -2.
All right.
How do you know if it's like 1 and 2 positive, negative, equal negative,
So what you got a graph? All right, Landon got something that looked like this. Is this something like what you got? This is not a polynomial, it's called a rational function. It's a fraction, a rational function. It's full asymptotes. Now, if you forgot that that asymptote was a 2, you could hit the trace button and just watch your y values as you go out this way. And what's happening to those y values? You should be noticing that they're getting bigger and closer to 2. So as you go off the page to the right, just hit your trace button, follow it out, watch those y's. You'll never reach 2. You're gonna get closer to 2 though. And so what are we gonna say? As we go to the right, we're getting closer to 2 from the bottom. Right? We're coming up toward 2 from the bottom of 2. As opposed to this kind of picture, which would still be getting closer to 2, but this would be coming in from the top side. And then, what happens over here? Well, that's exactly what happens over here, right? We get closer to 2 from the top side. Alex?
Does the horizontal asymptote, is it just the coefficient of the x
It
on
is.
top?
It is. Because if you think about, Alex, look at me. If you think about this problem, and you think about what you're talking about here, is letting x get ginormous. How significant, think of it as a trillion. 2 trillion minus 3. How significant is the 3? Not. How significant is the 1? Not. What really matters is I got 2 trillion over 1 trillion, which is about 2,
Okay.
right? But because of these two numbers, it will never be exactly 2. But the bigger x gets, the closer we're gonna get to 2.
Thank you.
All right? But even if you didn't know that, if you traced your curve, you should be observing that with your y values. All right? Okay, do the same thing with C. Without the calculator, do you see an asymptote at 0? And a horizontal at 0? Think about your problem, you guys. What's gonna happen to this fraction as x gets big? 10 over a billion squared. Really small, right? Now, is it ever going to actually be 0? No. But the farther I go, the closer it's going to get. So would you agree I have a horizontal here? Did your picture look something like this?
Yeah.
Makes sense that it would all be negative because you're squaring. So that's going to be positive. You're negative. So what are you going to tell me? The limit to the right will be 0 from the bottom, and the limit to the left will be 0 from the bottom. polynomial functions will never have that end behavior. Polynomial functions are always going to be shooting up or down into space. Got it? But other functions can have these specialized end behaviors.
Can you explain like going from the dot,
What?
the maybe, never mind.
It's 20 times 15.
Good, Sophia?
Can you explain like the negative, like how you put the negative above the zeros and then the two, how one's negative?
When I get closer to this line,
Yeah,
I can come into it from the bottom or I can come into it from the top.
okay, so,
Negative is the bottom,
okay.
top is positive. Okay? All right. The next page, the end is in sight. Look down at problem 4. Right there on that page that says the end is in sight. Look down at problem 4. Those of you that keep looking up at the clock, yes, the end is in sight. Number 4, the graphs of, that did not get you. The graphs of the functions g and h are shown. Which do you think is g and which do you think is h? Come on, this is not hard. We're on the end is in sight, problem number 4.
H is like the dotted line.
H is the dotted line, G is the solid line. And a surefire way for you to know that is, what does plain x cubed look like? Plain x cubed looks like this, right? What does plain x to the 5th look like? That. X to the 7th, that. When you start adding stuff on or subtracting stuff, that's when you get the curves. That's when you start getting the evenness. So compare the end behavior of the two graphs, it's exactly the same. The end behavior will be the same. Why? Because it's an odd degree polynomial with a negative leading coefficient. And it doesn't matter what else is in the problem. If you have an odd degree polynomial with a negative coefficient, you're going to be up, down. Number 5, which term in the polynomial seems to have the biggest impact on the end behavior, and why do you think this is? What's the only term we look at? The highest power. And again, this goes back to what I was just discussing with Alex. Why is that one the most important? Because when we're talking about end behavior, we're talking about x getting really big. And if you're really big, if x is really big, which is more powerful? X to the 7th or x to the 5th or x or 7th? What's the most powerful? That guy right there, right? That's the one that controls everything because he is the humongous thing when x is like a trillion. All right, back of that page. Number 1, check your understanding. Number 1, use limit notation to describe the end behavior of the graph. You can do this. Yes, those are arrows. Yeah. Use limit notation because we are grown-ups. That's what we do. What would you tell me about this? Positive, positive? What does that tell me about my graph? It is an even power, even degree, and a positive coefficient. Is it possible for this graph to have a degree of 5? No. is if you have a degree of 5, what do we know about your end behavior? Pardon me? Huh? I already have one thing. If I have if I have a degree of 5, what do I know about my end behavior? It's gonna be in opposite directions, so that can't possibly be. Which of the following terms, when added to the given polynomial, will change the end behavior? Check all that apply. Alright, so think about that for a minute. What is the end behavior of the original polynomial? The original polynomial looks like this. So this would be positive and this would be negative. No. Other way around, I got that upside down. This side is negative and this side is positive. From positive down to negative. So which term there, if I added it in, would change that? Maybe more than one answer.
Negative x to the 8.
You put a negative x to 8 in kids, what is that gonna do? It's gonna make these match, right? So yeah, that's gonna change it. 5x to the 7 would change it because then I would still have x to the 7th, but it would be positive. That's gonna change it. How about sticking 1,000 on it? Or negative 300 on it? Use limit notation to describe the end behavior of this thing. Come on, 2 more problems to do and we'll be done. What is the end behavior of number 4? What's the degree of number 4? The degree of number 4 would be 3. Leading coefficient is positive, so isn't this its shape? So on the left, we're down, and on the right, we're up. Everybody good with that? It's x cubed if you times it out.
How's it going up on the right?
This is it. This is our picture.
Oh, okay.
That's a positive odd. That was a negative odd fact, no problem. The graph of this has the same end behavior as the graph of what? I hear some A's, I hear some B's. Okay. Okay, they tried to trick you. Are your eyes open? Guys, what's the degree of the given polynomial? 6, and the coefficient is negative. So that in behavior is gonna match B, isn't it? That in behavior is gonna match B, isn't it? Yep, all right, that's it. You're gonna have your 1-6 homework due on,
Friday? No.
what's today, Thursday?
Oh, today's Thursday, so
Monday.
Monday.
1-6 is gonna be due on Monday. And then on Monday, or no, on tomorrow we'll do some extra review and practice. We won't cover any notes tomorrow. We'll just do practice with our graphing.